Monday, we talked about section 8.4, which is multiplying and dividing rational expressions. And this is when we basically are simplifying these expressions and finding basically a more simplistic graph of what they are. But we also have to worry about when we cancel things out, if we have some values that are in the original equation that we have to watch out for. So this section 8.3 is a pretty easy section. It's graph general rational functions, and then state the domain and range. It's a little different than 8.2 because these are simple rational functions and these are a little bit more complex. So what makes these more complex, you'll see, is that there's the quadratic involved, and that's what can make it a little bit more tricky. So let's go ahead and graph some of these and talk about what they look like. So here is Desmos. The first one is y equals 4 divided by x squared plus 2. So remember, just to kind of remind everybody, a rational function is just basically a ratio of one function over another function. So in this case, the top function is 4, okay, and the bottom function is x squared plus 2. Okay, so a rational equation, when you think of that word, it's like, oh, what's a rational equation? It's just a ratio of two equations. So this is a ratio of 4 to x squared plus 2. Okay. X squared plus 2 on its own is a parabola, but then the fact that we're dividing it by 4 kind of makes our graph a little bit interesting here, right? Okay, so what we want to do is we want to graph it. So we have a graph here, right? And then we want to talk about what the domain and the range is for our graph. So if we pop this into Paint, okay, the domain, remember, is all of our x's. So if we look at this, the domain appears to not have any holes in it. It goes all the way. It's a smooth curve. And this makes sense because if you look at your domain, what x's can you put in? It looks like we could put any x's in here and that they would work. The one watch out where you would have with the domain an x that would not work would be if for some reason we could make this bottom equal 0. If we made the bottom equal 0, then our function wouldn't be valid, right? But is there ever a value where x squared plus 2 equals 0? Well, that would mean that x squared has to equal -2. And we can't really do that. We can't square any number and get a negative number in the real domain. We can do that in imaginary numbers, right? But we can't do that in the real domain. So that means that our domain is all real. Okay. Our range is a little bit different though. Our range, remember, is our y. Okay. And our range appears to have an asymptote down here, right? When y equals 0. And it appears to have a maximum right here when y equals 2. So let's kind of think about why this is. All right, so if I have a really big x, like x equals 100, okay? If I have x equals 100 and I put it into my equation up here, I'm going to have 4 over 100 squared plus 2. Right? So I'm going to get basically a really big number at the bottom. No, that's going to have a 2 there, I think. I'm going to get a really, really big number at the bottom over 4. And so any number, like if you have a small number divided by a really big number, it's just going to get a really, really small decimal. But I can never actually get it to hit 0. So I know that my y has to be, it can't ever actually equal 0. Y has to be greater than 0. Okay, so I know that part of my range. On the top part up here, it looks like at 2, but can y actually equal 2? Well, let's see. This looks like that happens when x equals 1, or sorry, x equals 0, right? So when x equals 0, if I plug it into my equation, y equals 4 divided by 0 squared plus 2. So 4 divided by 2 is 2. So it looks like y can be a maximum of 2. So my range is that y has to be greater than 0 or less than or equal to 2, because it can equal 2 if x equals 0. So we have the graph to help us out, but we kind of have to understand why the rational function is behaving the way it is basically what we're doing. Figuring out why does it show up like that? What's making it behave that way? What's making my domain and range act like that? Okay. All right. Next one. That makes sense, Connor? Cool. All right. Get a little more tricky here. All right. All right. We have another rational function. So the top is 3x squared divided by x squared minus 1. So the tricky thing with these is make sure you type the formula in correctly, because that would obviously mess things up. All right, so we have a very cool looking function here. I think it looks cool, right? And kind of what we have going on is we have two parabolas that are competing against each other, right? We have 3x squared, and that's competing against x squared minus 1. They're kind of competing against each other to figure out what value of y you're going to get. I'm actually going to copy this and paste it again, and I'm going to use a function of Desmos that also is a function of your graphing calculator. So what I'm going to do is I'm going to it's the same exact equation, but the second equation I'm actually going to convert it to a table. Okay, so here you can actually see that they have values here, and you can type in any value. If I want to know when x is 100, what is my value of my function? It tells me in this table. So I'm going to leave this up here, and I'm going to go over to I'm going to print this out, kind of print screen, and we're going to talk about what the domain and range is. Okay, so here is Paint, and just looking at my graph, okay, before I even kind of dig in, I notice a lot of different asymptotes. Okay, I notice a horizontal asymptote. Oh, I wanted that to be green. Let's make that yellow really light. I notice this horizontal asymptote here that looks like something's up right when y equals 3. Okay. I also notice, oh, gray is better. There we go. I also notice it looks like there is some vertical asymptotes, right? Looks like there's one here when x equals -1, and it looks like there's one here when x equals +1. So I have these asymptotes going on, so that's really going to play into what my values for my domain and my range are. Okay, so let's start off with the, nope, I wanted that to be gray. There we go. Okay, so let's start off with the domain. Okay, so the domain is your x values. So if I look at this graphically, it looks like x's are good, x is good, did all the way through here. Excuse me. And then when I get to x equals -1, it looks like I have an asymptote. Then x's are good, and then x equals +1, asymptote, and then good again. So my domain, just visually by looking at it, I think is going to be all reals except x cannot equal, x cannot equal -1 or +1. Okay. And then if I go over to my table, this is confirmed. When I put in x equals -1, you can see it tells me it's undefined. Well, why is that? If I put -1 in here, -1 squared is 1, and 1 minus 1 is 0, and then I have the dreaded divide by 0. So that is an undefined part of my equation, right? The same with positive 1. If I put in x equals positive 1, 1 squared minus 1 is 0, and again, undefined. So that kind of takes care of my domain, right? Now if I look at my range, I'm going to write range in purple. Okay, start from the bottom. Looks like I got y values, y values, y values, y values, y values, and then I stop here when y equals 0. And then it looks like I don't have anything until y is greater than 3. So if I look at my graph, just kind of based off my graph, I think that my range, and this is going to be kind of funny, the range is going to be y has to be greater than 3. I don't think it's going to be equal to 3. Okay, but I'm going to double check that. Or y has to be less than or equal to 0. Okay, so what I'm proposing is that either my y values have to be greater than 3, so it never can actually be 3, okay? And we've kind of, this first part, y is greater than 3. So you see, if you pick an x value way out here at x equals 100, right? Your y value is still 3.00003. There's always going to be some component of that that's not going to make it equal to exactly 3. And if you plugged in 100 here, you're going to see you're going to get really close to 3. You're going to get 3.0003, but you're never going to quite get there. So I'm pretty confident that y can't be equal to 3. Y can't be equal to 3. It has to be greater than 3. Okay. And then I have this little section in here between x equals -1 and +1 where y can be a negative number. Now, I didn't do a good job with my chart, so I'm actually going to flip back over to Desmos really fast. And I'm going to put in some values that are between x is -1 and +1. So what happens when x is -0.5? And what happens when x is -0.25? And what happens when x is 0? Oh, so that's a valid point. When x is 0, that's a valid point, right? What happens when x is +0.1? So you can see it's actually putting these dots on here for you so you can see. So all of these are valid, right? They're all valid points, including when x equals 0, y can be equal to 0. So this is true that my range is y is greater than 3 or y is less than or equal to 0. All right, so that's the next one. Let's try a couple more and that will be it. All right, we have, I think we're going to have another competing one here. Let's see. Oops, that's not what I meant to do. All right, so we have y equals x squared minus 5 divided by x squared plus 1. So again, we have some competing parabolas. Let's see what this guy looks like. That's kind of crazy. It looks like a bird, a fancy, well, a not fancy bird that I would draw that's flying. Okay, so again, what I'm going to do with this is I'm going to take that same thing and I'm going to convert it to a table. So you do that by going up to this edit and then convert to table. Okay, so this shows you some key points along here. It's always helpful to put in what happens if I have a really big X, right? Oh, eventually it's going to get to 1 because it can't calculate it. We'll put in a really big X. We also know what happens when X equals that. So I think we have enough values to kind of figure it out. All right, so if I print screen, okay, it looks like I have, well, it doesn't look like I have any vertical asymptotes, but it does look like I have a horizontal asymptote. Oh, that's not what I want to do. right, at y equals 1. It looks like there's an asymptote there. And then it looks like my graph can never go bigger than -5. Okay, so then if I want to talk about my domain, right? My domain is my x's. And here it looks like I'm good with all my x's, right? So my x's are all real numbers. It doesn't look like there's any values in there that are going to, that are not going to be true. So why does this one have all real and the other one had some holes? Well, if you remember the last problem, it had a subtraction in the bottom, so we were able to subtract to get 0. Here, we're squaring a number and then we're adding 1. So whenever you square a number, you get a positive. Even if it's 0, you get positive 0, right? And then you add 1. So you're never going to be able, on the real number scale, to make this equal to 0. And that's what makes our domain all real numbers. Okay? So really, this bottom part controls the domain. Okay? The second part is the range, right? And the range is your y's. So the range for this is that my y has to be, we have -5, right? Y has to be greater than or equal to -5, but it has to be less than 1. Okay? And so my values of y have to be greater than or equal to -5. So that's this point here. And we verified with our table that when x equals 0, y can equal -5. Right? So that is true. That's why we have this equal to part of our equation. All right? And then we also verified with our table that even if we get a huge x number, if we go way out here on our graph, like we zoom way out, right? We are going to get really, really, really close to the number 1, but we're never going to quite get there to number 1. So that's why y has to always be less than 1, and it can't actually be equal to 1. Okay. Okay. So that was a pretty easy one. And then one more. I know. All right. So we have, oops. Y equals x squared. Oops, I have all my stuff in there. I need to delete all that. Let's start over. Y equals x squared minus 2x minus 2. Okay, so you see that that's your parabola there, but then we have a ratio divided by x minus 4. So before I even look at this, I see at the bottom x minus 4. So I know that when x equals 4, that I am going to have an asymptote there because that's going to make my equation equal to 0. So I can already see this is a really simple one to see where you're going to have some holes in your domain. But I'm going to go ahead and graph it, and I'm going to go ahead and make a table, and we'll talk about what the domain and range is. So that's that. Here is my table. And I'm going to zoom out a little bit so we don't miss the other part of our graph. Okay. And one value that I think is important is what happens when x equals 4. And then it's always good to do like 10,000, right? And let's also do like negative 10,000. Okay. All right. So this one's kind of an interesting one. Okay. So let me pull this over to print screen. All right, so this one's kind of an interesting one, right? We definitely have a vertical asymptote here at x equals 4. Okay, so let's just put that on there and let's talk about what the domain is. So let's start with that because that one's pretty easy. So the domain is all your x's, right? If you look at your graph, the x's go on forever this way. We've kind of shown this by putting negative 10,000 and positive 10,000, right? We've kind of proven that. Except there's one value right here when x equals 4 when it can't be true. And that makes sense because if I put x equals 4 in here, then I get divide by 0, and then my whole kind of equation blows up. So that's good. So the domain is that all reals except x, that's not an x, that looks like a k, x cannot equal 4. Okay, so domain is pretty easy. Now, range is a little bit more tricky, right? So if you notice here, and we haven't actually done this before, but there actually is an asymptote that's not a horizontal or vertical asymptote to this equation. Let me see if I can draw it. The asymptote actually goes like along here. So there's kind of a weird asymptote that goes on, and then there's a break in my domain and my range. Yeah, so there's a break in my domain and range. So I don't think I put all my values up on here. So if I'm talking about my my x and y values, or my y value for range, right? We have this break from this to here, and I actually didn't define it on here, so I'm going to go back to Desmos where I can actually click, right? And I have this value here that's my maximum, and I have this value that's my minimum. So I know that my graph kind of ends at those two values. I also notice that way out here when I get x to be a really big number, let's zoom out a little bit and see if my graph ever has any endpoints. Sorry for the crazy scrolling. So if I zoom out, I'm okay. The graph keeps going forever, right? When I zoom back in, like I have these values that are in between here, and I'm having like a little mind blank for a moment because I know there's an algebraic way to solve this, but right now my mind is just blanking for a moment. So what we're going to do is we're just going to go with the graphical values, and then on Monday I'll try to, I'm for some reason I'm blanking on the algebraic way to do it. So we know that our y's can be any value except they have to be either less than or equal to 1.551 or greater than or equal to 6.449. Okay, so if I pull that over here, I know that my range, okay, my y has to be less than or equal to 1.554, or my y has to be greater than or equal to, I think it was 6.449. And I'm having a little mind blank about how we're going to do that algebraically, but I will show you on Monday how we can figure that out algebraically. But you can see graphically that there's that gap there. Okay, so that's all I wanted to do today is to go over those because it's way easier to do it on here. So go ahead and try those problems and let me know if you have any questions. And that's all I have for today. All right. Good deal. I hope you have a good day. All right. Thanks. Bye.